Hey, this is Mr. Kim. We're gonna go over how to do curved mirror ray tracings right now too. So if you guys can, open up a curved notes file from our class and we'll get right to it right now. So the screen should look like this if you got the correct notes down. And just to start off, I'm gonna review our old kind of terms for virtual and real images. This is partially from a reading guide, also from other things as well too. But when we think about virtual and real images with mirrors, for plane mirrors, we've always had virtual images so far where the actual image is formed back behind the mirror somewhere. And so this is formed by a diverging light rays and formed behind the mirrors from plane mirrors as well too. And it's only visible when you're looking into the mirror. Um, that was always true for plane mirrors, but today we're gonna go into using curved mirrors, and we use them a lot for different applications as well too. And sometimes we will get virtual images, but other times we won't get virtual images. Instead, we'll get real images, and real images are formed by converging light rays, real actual light rays meeting together in real space. And instead of forming behind a mirror, they're formed in front of a mirror, and they can also then be projected onto a screen. So projectors forecast real images by projecting real converging light rays onto a screen. And so that's kind of a review notes for virtual and real images. If you need to jot that down, you can pause the video and make sure you have that in your notes there. But for today, there's gonna be three main rules we use to kind of have our ray tracings done successfully. So if you go down to the way bottom of your notes, this is kind of a review of what we want for our three rules for ray tracings with curved mirrors. We're gonna talk about light rays coming from an object going towards a mirror. That's the incident ray of light. And we're gonna have this thing called the principal axis as well too. That's just a line that's used for our reference that goes straight through the middle of a curved mirror. And we're gonna place all of our objects on the actual principal axis to kind of help us out and use that kind of rough estimate line to get our ray tracings done correctly. All right, so there's three rules we'll follow each and every time. The first one I'm gonna say is gonna be that we'll have rays of light coming in, going parallel to our principal axis, and we'll show that as well too. When it goes in parallel and hits a curved mirror, it reflects back coming out through the focus point. And the focus point's where all the light rays focus in on one single spot. If you watched the demo video yesterday, it was all in there as well too. Number two, it kind of is the reverse of that rule. If we have an instant ray of light going through the focus point and follows all the way to the mirror, then the reflected ray comes back out parallel to the principal axis. And then lastly, number three, if the incident ray goes to the center of the mirror, then the reflected ray follows that law of reflection. So we'll show these with different applications of different mirrors. And so let's just start kind of way above. I'm gonna begin with our convex mirror here, okay? And so if you want to jot down on this picture, this is going to be the shape of a convex mirror where the belly kind of comes out towards us. This is also called a diverging mirror. Diverging. The reason why is because once light rays come and approach this mirror, we'll have the light rays kind of diverge and go away from one another. And to kind of show that, here is an image that is on physicsclassroom.com, but we have an object shedding a lot of light on a mirror, and all those blue light rays approaching that mirror diverge out and away from one another. So if you look at the red reflected rays, they all go out and away from that actual mirror. So over here, we had three rules again, and I'm gonna kind of paraphrase them as we go through this guy. But first and foremost, this black line that's gonna be going right through the actual center of that mirror, that's our principal axis. And to make the actual ray tracings work appropriately for us, we're gonna actually put a dash dot, a reference line for ourselves, vertical. I think that's vertical for me. That's gonna help us kind of tell when the rays are going to change direction. And so I'm gonna erase every other portion of this guy here to show that that's a reference line we're using. That's not a ray of light I'm trying to show at all there. So there's our dotted dash line to kind of show when we're gonna change directions for our light rays as it approaches a curved mirror. Mathematically, it works a lot better. And it's hard to capture the curvature of a mirror on a small sheet of paper like this. So we're gonna use that guy as our reference point to change directions. And the first rule said, hey, we're going to begin at an object, and light rays are going every single direction you can think of. But there's one light ray that's going to go from that tip of the candle to the mirror, and it's going to change direction again at a reference line there, and it's going in this direction. Now, it's going to diverge out and away from the mirror there, so it's going to go somewhere out here, and when it diverges out, it'll be in line with that focus points down here. So the rule said every ray that goes parallel to the principal axis will then travel through the focus, and for us, it's actually the virtual ray traveling through the focus there. The reflected ray bounces off, goes in that direction, and to show that the reflected ray is going to have this virtual kind of path that our eye perceives it to take back behind the mirror, I'm going to dash that line back there so I know it's a virtual ray back behind the mirror that's in line with that reflected ray. That was the first rule. The second rule stated that kind of the exact opposite. Any ray of light that comes in towards the focus points of the actual mirror will come out parallel. And when that happens, we got a ray of light. It's going to go in line towards that focus point there, but before I can get there, what's going to happen is I actually have to change direction somehow as I hit the actual mirror surface. So I'm only going to trace my line that's going towards the focus point up to that black reference point we had before. And so the ray of light was going in that direction. And it's going to come out parallel as well too. And you can already see right now, those two reflected rays, when they're traced back, they don't ever converge in real space together. They're going to go out and diverge away. But where they will converge is somewhere back behind the mirror. And so here's my virtual ray of light from the reflected ray that my brain thinks is really there, but is going to be back behind the mirror. And that's another dashed line there. All right. Lastly, there's going to be another rule that we can use to kind of get our ray tracings done here. The last rule says I'm going to go from the tip of the actual candle to the center of the mirror. And this is kind of like what we've been doing with our plane mirrors. There's going to be our angle of incidence using my principal axis as our normal line. And it's going to come out with an equivalent angle of reflection as well too. So it comes out maybe like right to here. Now I'm kind of estimating right now, but there's our angle of reflection. And for this green path that we're taking, that's going to be me trying to show the law of reflection there, angle I equals angle R. Again, that light ray going down and away shows that all the light rays approaching this mirror from our candle tip, they're all diverging out and away from one another. So we do have an image. It's not anywhere in real space though. It's going to be back behind the mirror. And so there's going to be another dashed line that I'll draw for our reflected ray going back behind the mirror there. And what's kind of nice and neat is that you can see all three rays do show that we have one point of convergence, and I'm trying my best, but I want to redraw at that convergence points where all the light began from, which was the tip of our candle at the top. So I'm going to draw the tip of our candle there as best I can. Ooh, that's an ugly candle. And then the bottom of our candle was sitting on the actual principal axis like it was before as well too. It was on the principal axis there, it's still on the principal axis here, and there's a tiny small image. And actually this is going to be true for all convex mirrors. So if you want to make a little annotation for yourself, for all convex mirrors or diverging mirrors, same thing, the image is going to be behind the actual mirror there. And so when it's behind that mirror, I'm going to say that we call that guy a virtual image because there's not real light rays meeting in real space. It's the virtual light rays meeting up back behind the mirror. Besides that, we also have the image being right side up. So I'm going to write down RSU for abbreviations. And lastly, that's going to be smaller than the actual object that we have. All right, so just to make sure we're doing this well, we have a diverging convex mirror that's going to have that, oh, my screen went away. Small, tiny image there, okay? All right, And this is true all the time. If I can go to this quick simulation here, if you look with me on the simulation, I'm gonna have my objects, this time it's gonna be on the right side. Oh, my interactive's kind of going crazy right now. And ooh, it's gonna have that object there. And I'll make it bigger for us to see as well too. But the object's on the opposite side that we had for our drawing, but as I bring the object in closer and closer and closer, you can see the 3 rules that we've been doing as well too on this interactive. But that image that's formed is, first of all, always behind the mirror all the time, and it's always smaller, and it's always right side up. So the ray tracings are the exact same things that we just drew up, but here is showing smaller, virtual, sort of images. All right, so now I'm gonna kind of change gears and switch to a different kind of mirror. So I'm gonna go to a concave mirror where the belly kind of bells in. And so I'm gonna call this next diagram a concave mirror. And again, this is called a converging mirror because for this one, this kind of mirror converges all the light rays together. So if I go back to the physics classroom, I like this diagram a lot. I think this is it right here, yep. If you see on the left picture, if you send in all these rays of light that go in parallel to one another, they actually all kind of converge at one spot, and that one spot that they converge at is the focus point. And again, please do watch that video of the demos that Mr. Starzak did, I think that was yesterday, to show that focus point in real life with real light rays there. And likewise, if you actually send light rays through that focus point going towards the mirror, they all come back parallel, and those are the 2 rules we'll start off with for our ray diagrams here. So to our diagram, what I'm going to do is say, hey, my first rule that I had before was I'm going to think about where the principal axis is and drawing a reference vertical line that helps us with our ray tracings and tells us when to change directions when the incident ray hits that dashed black line there. So there's my dashed black line. My first ray of light will go parallel to the mirror. And again, like I'm gonna try go to the black reference line there so I know when to change directions, because showing curvatures on a sheet here is so small and hard to do. It'll kind of come down, and before we said parallel and do the focus points, well here, the focus point's on our side of the mirror, and there is our reflected ray. It went parallel to the principal axis, then it went from that changing points in the middle down towards the focus. The next rule said that I'm going to instead do the exact opposite of what I just previously did. I'm going to go through the focus first for the first ray of light. So there's my first ray of light going through the focus. And then I'm going to reflect back off of that surface, coming parallel to the principal axis. And you can already see there is a convergence point already for us. Which is going to be hopefully right about there. Let's just check though with the third ray. Our third ray says we're going to start from the actual candle tip, go towards the center of the mirror. And again, we're going to follow the law of reflection. There's my angle I. And if I draw the light ray going out at the same angle that my light ray came in, what's super nice is that we get a perfect point of convergence if I draw these angles exactly the same, angle R. So again, we're trying to show for the green rays of light equal angles of incidence and reflection there. So these 3 reflected rays do meet in real space. When that happens, we get an image. And the image is weird though because the bottom, if you can see from before, it's on the principal axis. So the bottom of this new candle, this new image will be on the principal axis. But the top though, it's going to be right here. So there's my candle's flame. Again, that's a pretty bad drawing. But if the bottom's on the principal axis, that means that the image is actually going to be upside down. And so there's my brand new image that's upside down, but it's on our side of the mirror. And that's where real light rays converge. So if that's the case, the image is going to be, first of all, a real image because there's real light rays meeting in real space. And you can actually project this onto a real screen then. For right now, I'm gonna say this is upside down. And USD just stands for upside down. And in terms of size, this one is smaller, but actually I'm gonna show you something really fast. The the size actually could vary. So size varies, it could be smaller, bigger, or the same size actually. And that's as long as your object is farther away than your focus points. And if that's the case, we'll have the sizes being bigger or smaller than the original object. So if I go back to our interactive here, this is simpler to see when I move the object back and forth, but here's my object. I'm gonna bring it back to our left side so I can see a concave shaped mirror. And when I'm really far away, the image that's upside down, you can see it kind of changing size as well too. It's really small, but then at certain points, it gets to be the same size, and then a little bit later, when it gets closer, it actually gets to be a little larger as well too. It's a huge image over here now, so the size can change from us being really far away, we get a small image, or the same size, or a little larger even right down there. But all the time, we have a real image that's gonna be upside down, and the size varies. Now something weird happens when I get closer than the focal point. So when I bring the actual candle closer than the focal point, our image actually starts to show up and appear on the other side of that mirror. And that's gonna be our last thing we do for today. And so back to our notes. For our last thing down below, for another kind of situation, so I'm gonna write down, this is gonna be a concave mirror again, but this time, this difference is that my DO, or the distance from the object to the mirror, is less than the focus point. We're inside the focus point. And in terms of our rules, we're the exact same things as before as well. So I'm gonna draw a principal axis already given to us. I'll label that at least. And I'll have a vertical line here. That's gonna tell us where to change directions. And so here's my dashed line. It indicates to me it's not a real line, it's a reference line. And so there's no real light rays going vertically up there. First rule, same as all the time before we've done so far. From the very tip of that candle, if I want to figure out where that candle's flame will show up as an image in this mirror, I got to figure out where all those light rays will converge as they reflect off the mirror. And so here's my first ray. You want to go in parallel, same as before. Hopefully these rules are getting boring now because you've heard them so many times. And then I'm going to go through the focus point. All right, I'll do that. So here's the focus point. I'm going that way. All right, so there's my ray going through the focus point. All right, second rule. Second rule says that any ray of light that goes through the focus point towards the mirror will come out parallel from there to the principal axis. And so I'm going to start at the focus point, and I need to make sure that the light ray actually goes through the point of interest of the tip of our actual candle there, and it's going again from the focus points towards the mirror. And then it comes out from there parallel, and you can kind of see it already. It's going to be way different than before because right now, those two reflected rays don't converge anywhere at all. So the two I just highlighted, right? They don't converge on our side of the mirror. They do show an image somewhere though. They show an image back behind the mirror. And so actually what I'm gonna do, like how I did in the very, very first case, is I'm gonna draw in these virtual rays back behind the mirror. And when I do so, I'm gonna dash these because again, these are not real rays of light I am actually showing. They're just gonna be virtual rays that we interpret there back behind the mirror. And then now we do have a convergence point. That's awesome. Just to check, let's just make sure this is right. I'm gonna draw in my third ray here, and I wanna make sure that like my incoming ray is gonna have an equal angle of incidence as it does with an angle of reflection. And I think we should be okay. I'm gonna eye this a little bit. So there's our angle of reflection there being somewhat equal to the angle of incidence there. And again, that reflected ray doesn't trace and converge with anything on our side, but that virtual ray does, right in the back there, okay? So there's where our image should be, and it made sense when we saw the actual concave mirror with an object close to the focus point. We had a huge image back behind the mirror, so I'm gonna try my best to draw this candle there, and this time it's much, much larger. The bottom still being on the principal axis like that. So there's my concave mirror with the object closer than the focus point. And so to kind of label off and tell you what's going on with this image, the image is definitely going to be behind the mirror, which means it must be virtual. This one is going to be right side up for sure. And lastly, this is larger than the actual object was. And so a lot of times, an application for these kinds of mirrors, or when you have a makeup mirror, you bring it close to your face, you can see your face a little larger because you have this awesome concave mirror where your face is closer than the actual focus point there. And that should be your ray tracings for curved mirrors. And so we had convex mirrors, concave mirrors where the object's farther than the focus points. Then lastly, we had concave mirrors where the object inside of that focus point. And I'm going to erase the highlighted portions here so it's a little easier to see. So there's our final diagram, okay? All right, thank you so much for tuning in. Please do email with any questions as well too. Have a great day though.